Oh my God. So Drew, we are very deeply sorry. I only now realized that I was not recording, but I wouldn't say you missed much. We looked at a displacement distance graph and we looked at a displacement time graph. Right. Yeah. So 1 over 0.02 equals 50.
Yeah.
Okay, so that's your frequency, 50 hertz. Mika, let me see if you actually understand it though. How much oscillations you have in 1 second?
Um, what oscillations in 1 second? Will it just be one?
Nah,
No, two.
nah, not two.
Okay, no, I don't understand.
I catch you, I catch you. All right. Remind me, what is the definition of frequency?
Oh, the amount of oscillations in a second.
Yeah. Let me try to understand it actually right now, Mika. The formula for frequency is 1 over t. What do you think the 1 represents? Well, it actually represents 1 second. Let me try to make sense of this right now, Mika. We see that 0.02 is the periodic time. So the periodic time is what? What is the periodic time?
The time for one oscillation.
So if one oscillation takes 0.02 seconds, right?
Oh, and I want to find out. Okay,
We want to find out how much oscillations you're having.
1 second.
Right, you put it over one. Yeah, that's how it is working on. That's how it is work. And you get 50 hertz. So that is telling you, okay, in 1 second, the oscillation, you're gonna have 50 oscillations. In 1 second, you're gonna have 50 oscillations. Make
Yeah.
sense? All right. All right. So if V is equal to 343 meters per second, find the wavelength. Is there any formulas that you know involve V and lambda? And you just find frequency,
Um,
so maybe that might be a hint.
D is equal to frequency by lambda.
Right? And they want us to find wavelength, right? Okay, if we want to find wavelength, we need to make that a subject of the formula. So, what are you thinking to do?
It'll be lambda is equal to V over frequency.
Excellent. And but those of you guys that don't understand why she did that, right now, wavelength is on your right hand side. And it's being multiplied by what? Somebody other than Ambika. Right now, wavelength is being multiplied by what? Somebody else. Nikolai, Danelle, Nabil, Shina. What is wavelength being multiplied by on your right hand side?
The frequency.
Exactly. So if it's being multiplied by frequency and I want to get rid of the frequency, what's the opposite of multiplying by frequency?
Yeah, the divide by F.
Exactly, you would divide by f. Such that it would cancel off. Yeah. Mm-hmm. So the answer for wavelength is just going to be v over f. Do we know what v is and f is?
Yeah.
Yeah, so we shouldn't have a problem, right?
No.
V is equal to 343 and the frequency is 50 hertz. What is 343 over 50?
6.86
Right? And what is the unit for wavelength? Could anybody tell me? Ambika, if you want to get tell me. Wavelength.
meters.
Anytime you see length, meters, right? Are you 100% confident with this question?
Yeah.
Yeah? Okay. Did you know this before? Did you ever wonder why it was 1 over t or no?
No.
Now it makes sense now, right?
Yeah, it does.
Nice. So let me just put on some captions here so that when you're looking at these notes, you wouldn't just be looking at gibberish. Give me a second. Right. So let me start off with amplitude. Remind me. Ambika, amplitude tells you the what?
The displacement from the equilibrium.
Ah, yeah, that's only maximum displacement. That's what we're looking for. Because, like, how high or low? Maximum. And if you're confused about the equilibrium, I just mean like that, like the zero. Right? That's what I mean. Right. What does periodic time tell us?
The time taken for an oscillation.
How much? Shall I be specific? So the time taken for one. Time taken for one oscillation. Think about physics, right? In physics, they like to see numbers. Yeah, they like it to be extremely specific. So the time taken for one oscillation and the practical example in this question. So, Amika, in this question, it's saying that the wave, how long will it take for one oscillation? In this,
Um,
so it takes, how much time would it take for one oscillation?
0.02.
Yeah, and you saw that right? In point zero 0.02, there's one oscillation. Cool. So it takes 0.02 seconds for one oscillation. And we know that that is what the periodic time represents. Nice. And frequency. What is frequency, Amika?
The amount of oscillations in a second.
Right. And in this specific question, in this specific question, what could I infer from it?
Um, the frequency would have been 50.
But what I mean though? What I mean? How that helping, man? I want what I mean.
50 oscillations in a second.
Right. You okay with that?
Mm-hmm.
Cool. And you understand that wavelength is just the length for one full oscillation, right?
Yeah.
Cool. Nice. So guys, how we feeling? Like everything makes sense or nah?
Yeah, everything makes sense.
Okay, cool. I also want to point out something else. If wavelength is equal to V over F, would you say that wavelength and frequency is directly proportional or inversely proportional? If you had to look at it. I mean, if you all remember proportionality, and this is a maths thing, yeah? But we did this a lot when we was doing only gas laws. Nikolai, when I say directly proportional, what does that mean? Like if one go up, what I mean about the other one?
That mean the both just affect each other when they make a change. So if one go up, the next one will move.
If one go up, the other one will go up, right?
Yep.
Because they're directly related. If they are inversely proportional, then if one increases, the other one would.
Nah. If they're not directly proportional, the other one would.
The other one would what?
If they're directly proportional, then both of them go move. But if they're not directly proportional, then one go move and the next one wouldn't.
That doesn't necessarily mean that it wouldn't. It will move, but like at a different rate. Um, but if it's inversely proportional, that means that if one goes up, the other one would.
come down.
Exactly. So let's see if that happens over here. So you probably notice something, right? This looking real close to something. Like if I tell you that wavelength and frequency are inversely proportional, wouldn't I write wavelength is proportional to 1 over f? And we learned that when we were dealing with the gas laws.
Yeah.
And what would I write in the next line? Think about the gas laws when he was doing that. Yeah, they would say wavelength is equal to. Guys,
Generally, it would
think
be
from the gas laws.
1 over F and F over 1.
Nah, that would be K over F. Let me show you exactly what I'm talking about to jog your memory. Where are they, boy? Watch. So Nikolai, in this example, look at this, right? Look at this from Nikolai. Um, what would you infer from pressure and volume by looking at this? Would you say that they're directly proportional or inversely proportional?
Directly proportional.
Nah, inversely proportional. That's inversely proportional because when one, okay, Nikolai, if V, think about the pressure and volume. If I put a number here, right? If I put a big number, like let me just say 100,000. Do you think 1 over 100,000 is a big number or a small number?
A small number.
Extremely small. So when the volume increases, the final answer gets smaller or bigger.
The final answer is smaller.
Exactly. So when the volume increasing, the pressure what?
Decreasing.
Yeah. So I hope you understand that. So like back to this, right? And I say it's an important point to talk about. Because did you know that wavelength and frequency are inversely proportional or no? Because did you know that? That wavelength and frequency are inversely proportional?
Yeah.
Yeah, okay. You'll see what I mean when we look at the electromagnetic spectrum and we compare any wavelength and the frequency. So I'll make a little note about that right now. Right? So wavelength and frequency are inversely proportional. So Nikolai, let me try to understand this, right? So Nikolai, according to what I'm saying here, if the wavelength goes up, what is happening to the frequency?
The frequency will go down.
And if the frequency going up, what happening to the wavelength?
The wavelength will go down.
And that is what inversely proportional means, right? Opposite. They have like an opposite relationship. So to signify that, this is what I'm gonna do. Um, if you want to prove it, this is what I would tell you to do. So you could say that lambda. Okay, and since they are inversely proportional, would I say lambda is proportional to f? Would I say that? Would I say lambda is proportional to f?
See that again?
Okay, if it's inversely proportional, would I just say that would I write that they're directly proportional?
No.
No. Nikolai, this is not true, right? Because if I write this, and if this get bigger, this will get bigger. Okay,
Yeah.
think about this as an equal sign, right? Just think about it as an equal sign. If I say f is 1,000, n is gonna become 1,000.
Yeah, this will become 1,000 too.
if this turn out if this turn five, and wouldn't this turn five?
Yeah.
But that's not true, right? Because we know it's an inverse relationship. So like if one goes up, the other one has to go down. So this is not true. If it's an inverse relationship, I'll write lambda is proportional to one all over. Anybody remember?
Wait, say that again?
It'll be one over f. If it's inversely proportional, then it's going to be wavelength is proportional to 1 over f. It wouldn't just be wavelength is proportional to f. I would need to write it as 1 over f because it is inversely proportional. So in the next line, what would I write, Ambika? If we doing this strictly like from maths, I would say wavelength is equal to what? I would need to introduce what now? The constant of,
Proportionality.
right? So wavelength would be equal to what?
K
K over,
F.
yeah. Now we know that the formula in physics is it would be wavelength is equal to v over fn. Yeah, and that's what we know in physics as the formula, right? Yeah or no? If I use v is equal to f lambda and I were to divide both sides by f, wouldn't I get that formula? Wouldn't I get lambda is equal to v over f? Do you all understand this? Like this is the formula in physics, yes or no? Hmm, don't know.
I understand it so far.
Yeah.
All right, so I could see that, right? So I mean, if I compare this and this, wouldn't k just be v? I mean, it's the same thing, right? Wouldn't k just be v? K could be anything, right? But
Yeah.
in this instance, K is V. K is V. That's what we see, and that is what we are seeing, right? So I mean, it's nothing too different. The whole point of this is to show you that um okay, I feel like I'll understand it if I give Ole a practical example. I feel that's the only way I'll properly understand it. So let me give Ole a practical example. And he'll tell me if you understand this. So, Nikolai, doesn't this look almost identical to this? Doesn't it look identical?
Yeah.
Yeah, what's the only difference?
The sign one is K and one is V.
Right, but they could be the same. So, K is actually equal to V. Like, all right, when we was doing Hooke's law, right? When we were doing Hooke's law, does anybody remember Hooke's law over here? Does anybody here remember Hooke's law? Anybody? Ways, boy. Guys. Anybody? Hooke's law. Hooke's law. I don't know. Okay, now you wasn't there for that. I'll be unfair to ask you. Mika, you remember what Hooke's law is?
Not really, I know.
Oh, okay. Entering Hooke's law, we were saying that force is proportional to extension. Like you have a spring, right? And the more force you apply, the more you go extend. Think about it. Please, boy. Nikolai, I think I'll listen that. Okay, I did that with my class at the start, and you guys joined recently. I think that's why you're not familiar with Hooke's law. But like Nikolai, that makes sense, right? If you have a spring, any more force you apply, you go extend more.
Yeah.
Yeah, so force is proportional to extension, so then I would write F is equal to KE. But you see, K actually represents the stiffness of the spring. So, guys, the point I'm trying to make is K could be anything. K could be absolutely anything, right? it just linking one thing to the other thing. It could be anything, right? In the instance where you have for wavelength and frequency, K actually stands for the velocity. So let me give you an example, right? Let's consider two scenarios. Scenario one and scenario two. So Nikolai there.
Yeah.
All right, so Nikolai, let's just say in scenario one, we have a frequency of 1 hertz and we have a velocity of 5. All right, so Nikolai, if this is the case, right? When I find for wavelength is gonna be V over F, right? So what is V?
V is 5 meters per second.
And the frequency is?
1 hertz.
What is 5 over 1?
5
And the wavelength is? What unit?
meters.
Cool. Now let's try something else, right? So we're gonna change the frequency. Nikolai, what you want me to do the frequency? You want me to increase it or lower it down?
Increase it, yes?
All right. Let me increase it to 100 hertz. And I'm gonna keep the velocity the same. So if I do this, it's going to be V over F, right? So it's gonna be the 5, the same 5 over the what? 5 over what? It's gonna be 5 over what, guys?
5 over 1.
5 over 1? No, where's the new frequency in scenario 2?
Oh, 5 over 100 hertz.
Right, where's 5 over 100?
20.
Nah, nah. Could 100 go into 5?
Nah, that my bad. That my bad.
Yeah, you gotta be careful. What is 5 over 100?
0.05.
Ah, let me compare something, right? So okay. Let's get to the bottom of this. In which scenario was the frequency more? Tell me, guys, in which scenario was the frequency more? Scenario one or scenario two? Which one was the frequency higher? Ambika, in which scenario was the frequency higher?
In one?
In one? What was the frequency in
Wait,
scenario
no.
one?
In two.
In two, Nikolai, where was the frequency higher?
2.
Right. Okay. So scenario two will get a point for frequency, right? Had the higher frequency. Which one had the smallest wavelength?
2.
Scenario one or scenario two?
2.
It's two. So Nikolai, you notice that this scenario had the higher frequency, but the what?
But the lower wavelength.
Exactly. So Nikolai, just from seeing this, you're seeing that if you increase frequency, what happens?
The wavelengths become lower.
Exactly. Do you understand this?
Yeah.
Right. All right, so as frequency increases, the wavelength what? What happens to the wavelength?
Decreases.
And do you understand why I'm saying that this is an inverse relationship now?
Yeah. I
Yeah,
understand
because
now.
if one going up, the other one dropping, right? Okay, I I feel like I'm at like a crossroads. Do y'all want to do lenses? Tell me, do y'all want to do lenses or do y'all want to do continue with these kind of things with waves? It's in the same topic, but let me know. Do y'all want to continue in this type of direction or do y'all want to do lenses? Let me know, guys. Guys, are you hear me?
Well, I don't know about anybody else, but I would like to move on to lens.
Okay, what about the rest of you guys? Nikolai, Bika, Nabil, Shina. Don't let Danelle give you a bias, right? I want you to speak from your own opinion, like what you want, like what you believe in. Nikolai, lenses, or you want to continue in this direction with longitudinal waves and EM waves and thing.
Nah, I feel like I getting hang around the wavelengths and thing already. You think I just go over and need to go anything and switch it up. Get some practice.
Okay, so you want to continue or you want to move on to lenses?
Yeah, we'll continue. We'll move the lenses.
Okay, I just tell me one, continue or move to lenses. I hear you say both just now.
Nah, say lenses.
Okay, I hearing two for lenses, I hearing one for continue. Ambika, you want to continue in this direction? To cover things like, let me show you what the other things are in this direction. So if we go in and if we continue in this direction, we are going to look at transverse waves. We're going to look at all the waves in the EM spectrum, and we're going to look at the same relationship here. You know, frequency is inverse. We already did that. Um, and you're going to look at this. We're also going to look at longitudinal waves, constructive interference, destructive interference. That is how that direction would look like. It's not
Okay.
lots.
I want to do waves because I have an exam on it on Monday.
Okay, so you want to continue?
Yeah.
Okay, I need a tiebreaker. Actually, since you have an exam on it, I feel the best thing to do is just continue, yes? All right? Since you have an exam on it. I mean, we already kind of understand that wavelength and frequency are inversely proportional. We could just continue, right? Danelle, did you do physics before?
No, but I decided to teach myself because I have an exam in May, June.
Okay. I see.
Yeah.
So there are two types of waves, right? There are two types. There are transverse waves, and does anybody know the other type of wave? Oh my God, do you know the other type of wave?
Longitudinal.
Right. I just always type myself spelling this, but I believe it's Longitudinal. I believe that's the correct spelling. Longitudinal. You check that for me. Don't like English. Right, longitudinal waves. So let's start off with transverse waves. It's probably wondering, well, so what the hell is a transverse wave? What is that? What? Transverse? What do I even mean? So this is an example of a transverse wave. So Ambika, notice that the guy is moving the spring up and down, right? Seeing that?
Yeah.
Okay, he's moving it up or down. But is the energy moving up or down? Is the movement of the energy up or down?
No.
No. Nikolai, Danelle, Nabil, Shina. If you move a spring back and forth up and down, wouldn't it propagate? Wouldn't it go in this direction?
Yeah.
Nikolai, be honest with me. You understand what I'm saying there or no?
Yeah, that's what I'm saying because when you move it, the direction that you're facing and where you're moving, so we move that way.
Exactly. Like if I move it up or down, wouldn't it transfer the movement in this direction?
Yeah, you know, saying?
Okay, so you see, what I love is that all you do, like if all you do understand something, all you go tell me I love that. I'm happy that we create that environment. So Nikolai, imagine you have a spring, right? Or like a long slinky, and you know that slinky?
Yeah,
Right. If you move it up or down, wouldn't the movement be transferred forward?
yeah,
Yeah, think of like a rope. And when you like sling a rope, it go like do that, and it go move forward.
yeah,
Yeah, and then it go like hit and it go return back. But when you like whip a wave, like okay, when you whip a piece of where's that word again? Rope. When you whip a rope, or like even like what's the word I'm looking for? You could swear English is not my first language. Uh, what is it called again? Skip rope. A skip rope. That's what it's called it. Ambika help me out. Skip rope. And that's like when you jump on.
Yeah.
Yeah, like if you and you see like these things where the people like moving the rope up and down. When they do that, and the movement is in the opposite direction. I mean, what's the opposite? I mean, like it's perpendicular to how they're moving it. So, Ambika, if you're moving a spring up or down, the movement is going to be carried forth in this direction. Can we see that it's 90 degrees to each other?
Yeah.
Right, and now let me know if you're seeing that. So like this guy is moving his spring up or down, but it's creating a wave and the wave is moving forward in this direction. Then now let me know if that makes sense or no.
Yeah, that makes sense because I'm picturing one of them slinkies
Yeah, yeah. When you move the slinky, it is move up and down, or like it is like carry the energy moving forward.
moving forward.
Yeah. So like it go rise here, then it go drop here, then it go rise here, then it go drop here. So it's carrying the energy and it going forward. So the propagation of energy is perpendicular to the movement. So I'll write the definition, but hopefully you can see that. So in transverse waves, right, the displacement of particles is perpendicular of the wave. Right. Right, so you guys can copy that down quickly. So Danelle, you're probably looking at the diagram and you're probably looking at the definition and you're saying, huh, okay, I get the perpendicular part. You get the perpendicular part or no? You get that
Yes,
part?
I did.
Right. So that part, like you see, they're moving up and down, and
Right.
the direction it's moving in, the movement of the energy
Forward.
forward.
Mm-hmm.
So that we understand the perpendicular part for sure, for sure.
Mm-hmm.
What might confuse you is fancy words like propagation,
Mm-hmm.
displacement of particles. What is that? What I mean?
Like,
So
does it mean like when you say, okay,
yeah, tell me. Let me see if you can figure it out.
like when you say like displacement or propagation, does it mean like it's spreading out or no?
I wouldn't say spreading out.
Okay.
Yeah. Um, so don't know if I'm moving my hand up and down, think of it like okay, think of this as the displacement of particles. When you move
Mm-hmm.
up or down, aren't you displacing space? Like you're moving now. You're moving your hand up or down. You're displacing. Like, okay, if you have like an equilibrium point and you move your hand up or down, aren't you having a displacement?
Yeah.
Okay, think about that again. So
Uh-huh.
when we were drawing the waves, right?
Mm-hmm.
Zero was the equilibrium point, right? And then the
Right.
wave would I go up and it'll go down.
Mm-hmm.
You could draw like um a, let's do it again, like a relation. It's very
Mm-hmm.
similar because watch over here, this will be the displacement, right? Like from the equilibrium up, then from the equilibrium down. When you move your hand up or down, aren't you like aren't you displacing your hand? Like you're moving your hand, right? So you're moving it
Yeah.
from a position, and the hand doesn't have to be moving the spring. Something else could be moving the spring. But the point is you're displacing particles. Like by doing
Okay.
this, you are displacing particles, right?
Okay.
Right. So I know it sounds a little confusing, but just think of it like this. It's your hand and you're moving up or down, so there's some displacement. So you're displacing particles, right? So in transverse waves, the displacement of particles, which is what you're doing here, you're displacing particles, is perpendicular to the propagation of the wave. So propagation is just simply, okay, what do you understand by propagation?
For
If you
me,
had, yeah, if you had to understand what propagation is, what would you say it is? What does it sound like it is?
I'll have to look that up in the dictionary.
Okay, here what, right? Check this out. So I just tell you that displacement of particles would be this part. And now they're
Yeah.
talking about perpendicular, so over here, and we talked about this already. So where's the only thing left to cover?
Oh, the distance?
Not the
I
distance,
mean,
but the movement or the energy. Ah,
okay.
because we didn't cover this yet. So propagation of the wave is just a fancy way for saying the direction in which the wave travels. That is what it means. So you see this over here?
Direction. Okay.
Direction in which the wave travels. So Danielle, if I displace particles up or down, because you're moving up or down, you're displacing particles. Like think of like the think of the environment we're in. If you move your hand up or down, you're displacing particles in the air, right?
Mm-hmm.
So by me displacing particles up or down, my slinky is going to move in the direction perpendicular to my displacement. So I am displacing the spring up or down, but the propagation of the wave is perpendicular to that. And the propagation of the wave is just simply the direction in which the wave travels. So do you understand that
Mm-hmm.
the wave would travel? Yeah. Nah. Do you
Okay.
understand that
I
the
understand.
it makes perfect sense now, right?
Yeah.
Okay. Ambika, it makes sense for you now?
Yeah.
Okay, good. So you understand that this red axis here, you can think of it as the displacement. And this blue line over here, you can think of it as the what? In terms of the definition. So this corresponds to displacement. What do you think this could correspond to? Give me a guess, Ambika. Give me a guess. Throw something at me. Not literally. I do a headache. Yeah, don't throw something at me. But
Yeah.
like, say that again?
Propagation.
Yeah, yeah, the propagation, right? Because that's the direction in which it travels. So this is the propagation, the direction in which the wave travels. And yeah, you can clearly see the perpendicular part. This is the perpendicular part. Perpendicular just means right at a right angle to 90 degrees. Nikolai, let me know if you're confused or if you understand what's going on.
Nah, understand what going on.
Okay. Um, Ambika, you probably would have got a similar definition in school, or not?
Yeah, I did.
Yeah. Did you feel like you fully understood the definition? Or were you just going with it?
No, I understood.
Okay, that's good. I'm glad to hear that. So let's continue. You're probably wondering, well, sir, you could give me some examples of a transverse wave? I don't know what a transverse wave. Well, I kind of know what it is now, but long story short, all EM waves, all EM waves are transverse. So you're probably wondering, okay, what is EM? Could any of you guys make a guess? EM.
Electromagnetic.
Yeah, right. Guys, copy that down. Right. Do we understand this or not? Now, another example would be like water surface ripples, like waves in the ocean. Another example would be like seismic waves. When I say seismic waves, all you know is a seismic wave? Or not? Do you know what a seismic wave is? Yeah or no?
So what was the question?
Do you know what a seismic wave is?
Oh no.
Nah. It kind of
Mm-mm.
sound like it kind of sound like a what? Something for a what?
Like a
Seismic.
earthquake?
Yeah, exactly. It's an earthquake,
Mm-hmm.
right? So let me show you what that would look like. Show you what that would look like. So example would be all EM waves are transverse. Another example is a S-type. Wait there. Let me get the exact thing for you. Mm, right. Yeah, so seismic S waves. And this is caused during an earthquake. Did any of you guys do geography here? Or I mean, once saying did, that's not making it sound ancient. Are any of you guys doing geography?
I'm doing geography.
Oh, look at tectonic plates and how it like sliding on type of
Yeah.
earthquakes. Well, I don't think I'll learn about S waves and P waves and whatnot.
No, we just know it's seismic.
Ah, okay, okay. Well, let me show you what a S wave would look like. Is anybody here in need of a Casio calculator by chance? Oh, no.
Yes, how much you selling it for?
I gonna give away selling.
Oh,
Oh, these are already my students. Give it all, yeah. Yeah. Let me, okay. Can I download this video? No, I can't. S seismic wave. Well, when I come down south, I gotta give it to you. Ah, bet. Nice. Nice. Will it, please, will it move? Let's see. Ah, look it moving. Let's go. Let's go. All right, nice. I want you all to look at this, right? Are you seeing that? I'm wondering if you're seeing that.
yeah,
Yes,
I
sir.
see.
Yes.
Yeah, are you seeing that, right? Like, watch. We displace the particles, so like it move up, and that cause a ripple effect throughout. It cause a ripple effect, and it just being it propagating. Like if I shift over here, it's gonna propagate throughout. Are you seeing what I'm talking about or not?
Yes.
So like, okay, that's good. That's good because the particle motion. Look at the particle motion. You see that the particle motion moving up and down. Well, let's see now, right? It moving up and down, and the propagation is in this direction. It's perpendicular. And this is our S size. This is our seismic S wave. Then now, like, it making sense, right? Like, you see how it move? Wait, let me observe that again. So this is a particle here. Look at it. Look at it. You see how it moving?
Yeah, seen it.
It moving what? In what direction?
The same up and down
Yeah.
um motion
It moving up and down, but the wave traveling
forward.
exactly. Exactly. So it's a transverse wave. Yeah. Cool. So let's look at all the EM waves now. So I remember it like this. So like rich men in Vegas. Um, Ambika, yeah, well, you learn like this or not?
For what?
To remember the
Like the different types of waves?
yeah,
I don't know what acronym, you know.
you use acronym.
No.
I see. Rich men in Vegas use expensive gadgets. This is not mine, eh? I got this from my teacher. Big up, Suka man. I wouldn't know who that is, but big him up, sir. This is not mine. This is not. I don't claim that this is mine. Right? So rich men in Vegas use expensive gadgets. So let me start off from the top. Radio waves, right? Radio waves. Okay, what type of wave do you think starts with M and you find it in your house? Tell me, guys. Guys, M. M. What kind of wave? You can think about that with M.
The microwave.
Yeah, microwave. That's it, man. That's it. All right. All right. What about I? This one might be a little hard, but like when we were doing when we were doing the greenhouse effect
So
with glass.
infrared rays.
Yes. Remember I mentioned short wavelength radiation and I said that would mainly come from the sun. Well, it would come from the sun, and that's typically in infrared. Yeah. Okay. V. The best hint I could give is you could see it. You could see it. You could see it. Amika, you could see it.
Visible.
Yeah. Visible light. Right. You. Yeah, this is like to protect you from the UV rays. You would wear like sunglasses or like um or
Say UV.
yeah, UV. Ultraviolet.
Yeah, ultraviolet.
Right? And X. X1.
X-rays.
Yeah. And last one, dangerous. It's very dangerous.
Gamma.
Yeah. Now, guys, we just learned, we just learned that wavelength and frequency are what to each other. They are what to each other.
It's functional.
Yeah, we just learned that they are inversely proportional, Nikolai. And we learned that if you increase one, it would decrease the other one,
Yeah.
right? Inversely proportional. All right. So, Nikolai, if I have a really large frequency, think I'd have a what do you think I'd have? If I have a
You
huge
have
frequency, I would have a what?
a small wavelength.
And because I don't know if you ever think about it, right? But if you have a very large frequency, doesn't that mean you have a lot of oscillations in a small amount of time?
Yeah.
So if you have a small, if you, okay, if you have real oscillations in a small amount of time, and the length for each wave would get smaller and smaller and smaller.
Yeah, it would.
Yeah, so that's like the practical way you could see it. Nikolai, I don't know if you catch what I'm talking about, right? But watch this. Okay, Nikolai, which one looks like it has a greater frequency? Wave one or wave two?
Wave 2.
Okay, what about the rest of you guys? Which wave do you see occurring more?
Two.
Two, and everybody can see that. Okay, and which one looks like it has the bigger wavelength? Which one has the bigger wavelength?
One, two.
Let's see enough for yourself, right? In one, this would be one wavelength. But for two, this is one wavelength. Do we understand it visually? Do you understand why if frequency increasing, the wavelength would get smaller?
Yes.
Bet. It's a good thing you could see it. So let me think common sense wise. Mm, anybody you know that radio?
Yes.
Okay. And time radio waves is travel far.
Mm-hmm.
So out of these here, which one do you think has the biggest wavelength?
The radio waves.
I would agree, right? I would agree. So the radio waves has the largest wavelength. Because that makes sense, right? Because if we're talking about a radio wave, doesn't radio waves travel far?
Yeah, they do.
So I guess you could think about it like that. They have to travel far distances, so like large wavelength. And if it has the largest wavelength, inversely, what would it have? Think about it, guys.
Lowest.
It would have the what, Amika?
Lowest frequency.
Do y'all understand that or not?
Yes.
Because Nikolai, when when the wavelength, okay, Nikolai, do you understand that if one goes up, the other one will go down?
Yeah.
So like if it have the biggest frequency, the largest frequency, it would have the what? The smallest frequency, the lowest frequency. That makes sense, right?
Yeah.
Okay. And if this has the largest wavelength, what do you think this go have? So what has made gamma rays so deadly is the fact that they could basically penetrate anything. Now, Denel, if something could penetrate through anything, do you think it has a big wavelength or a small wavelength to pass through everything? This is how I always remember it, yeah?
Mm-hmm.
Denel, you there? Yeah, Denel, if you want to be able to penetrate through matter, you want a large wavelength or a small wavelength?
Awesome.
Small wavelength, right?
Small one?
Yeah. So this is gonna have the smallest wavelength. But if it has the smallest wavelength, what do you think that's gonna mean for the frequency?
Frequency. Be higher.
Gonna be the highest frequency. And everything else is gonna fall in. Right? Are we okay with that? Let me know if you guys are okay with that.
Yes.
Yes, sir.
I bet. Let me tell you the frequency of the waves now. So frequency, I don't remember this off the top of my head. So frequency of EM waves. I go to Google and Google tells me cool. All right. So if we're talking about radio waves, right? Radio waves is going to be 10 to the power 3. So what I'm seeing here. Right? So radio waves has a frequency of 10 to the power 3. Wait, so that's a wavelength. So it has a wavelength of 10 to the power 3. Okay, but I want frequency. Master them. Yeah, I want frequency. That's typically what they want. So that's going to be 10 to the power 4 hertz. Mm, okay, this is not what I want. This is not what I want. Come on a second. You see, the thing is, there's a range. There is a range. That's the thing. So you're gonna see like different answers everywhere you go, because there's a range. I believe in CSEC, they just ask you to sort it. I don't think they expect you to know like the specific frequency. But in my notes I should have the specific frequencies that correspond to. Amica in school, you had to learn the specific frequency, like you had to memorize that.
No, just the order.
Yeah, just the order. I don't think they gonna make you do that. That'd be kinda crazy expectations. And like I say, it's a range. Where is it? Yeah, I have it over here. But what I have over there, I believe that is the wavelength. I believe that's the wavelength I have there. Yeah, so let me put it in. So what I'll put in for you guys, I'll put in the wavelength. for the new wavelength. Where's that boy? Mm. Did I lose the notes? Where did that go? Give me a second. Okay, here it is. Yeah. So I'll put down the wavelength for you guys. So the wavelength for radio waves, right? So lambda here is going to be equal to 10 to the power 3. And that will be meters, right? 10 to the power 3 meters. The wavelength for microwaves is going to be 10 to the power minus 2 meters. The wavelength for infrared is going to be 10 to the power minus 5 meters. For visible light, it's going to be 0.5 by 10 to the power minus 6. And well, for ultraviolet, it's going to have a wavelength of 10 to the power minus 8 meters. For X-rays, it's going to be 10 to the power minus 10 meters. And for gamma rays, it could be 10 to the power minus 12 meters. Danelle, logically, it kind of makes sense, right? If the wavelength's so small, it makes sense that it could like go through anything. It could penetrate through anything. And there's also a relationship with energy here using Planck's law, but they wouldn't see that unless you do lower six physics. How much of you guys planning to do physics in Cape? Well, that's a long time from now, but like how much of you guys planning on doing that? Because you planning on doing Cape physics?
Yeah.
Yeah, well,
Yeah.
you will see that. You will see Planck's law. Right. Ambika, if you had to say, which one do you think has the most energy? Ambika, which one is the most dangerous here?
Gamma rays.
Yes, that one would definitely possess the most energy. And I kind of giving you like a preview into Keep. This is called Planck's law. E is equal to hf, where h is Planck's constant, E is energy, and f is frequency. Planck's. So like Ambika, in this instance, you would say that energy is what to F? Directly proportional or inversely proportional? What kind of relationship that looks like?
Inversely.
Nah, that's directly proportional.
Oh,
Because watch, if you plug in a big value for F and you multiply it by a number, wouldn't E go up?
yeah, it would.
If you pass small value here, wouldn't this drop?
Yeah.
Yeah, so this is a directly proportional relationship. So based on this, the greater the frequency, the what? All right. The greater the frequency, the what?
Increase the energy.
Yeah. Cool. So rich men in Vegas use expensive gadgets. So Ambika, tell me. So tell me the acronym. So
Rich bakers use expensive gadgets.
right, and if you were to call it out for me, the first one would be what? The first one,
Radio wave.
radio. Then it would be what?
Microwaves.
Right? What next?
Infrared.
Right? Because rich men in, yeah,
Um, Visible.
right,
Ultraviolet.
right.
X-rays and then gamma rays.
And guys, quickly tell me which one has the highest frequency? Okay, which one has the smallest wavelength then? Which one has the smallest wavelength? Key. Which one has the largest wavelength? Guys, anybody? Which one has the biggest wavelength?
Radio waves, sir.
Right. So if this have the biggest wavelength, then it would have the what frequency? Somebody tell me.
Smaller frequency.
Right, lowest frequency. Okay, and if that is the case, then gamma would have the what wavelength? It is the biggest. What do you
The
think it has?
smallest wavelength.
Exactly, smallest wavelength. Right, and this is going to have the highest frequency. Okay, could you all remember that? Like rich men in Vegas use expensive gadgets?
Yes, sir.
Bet. And you know that radio has the biggest wavelength, so it has the lowest frequency. And if you could figure that out, then you should be able to figure out that gamma is just the opposite, and everything in the middle falls into place. Okay, great. Now, a very, very important thing that I needed to understand. Everybody here, I need you all to understand that all, don't say I didn't tell you this, all EM waves travel at the speed of light. Guys, I can't stress how important this is. So for all of these waves, V is equal to what? Does anybody know the speed of light? That'll be 3 by what? Does anybody know the speed of light? 3 by Ambika, you know?
No.
No.
All right, 3 by 10 to the power 8, right? Meters per second. So every single wave here is going to travel at the speed of light. I can't stress this enough. When you're doing these types of questions, they will never tell you what speed it travels at. They expect you to know. So before I go, I just want to do one question because Amika, you said you have an exam on this. So did you do up to this point in your school?
Yeah, it's it.
Did you do lenses yet?
No.
Nah, okay. Let me get a question for you quickly. I watch like over here. They say state one property of an electromagnetic wave, right? And I said is that all EM waves are transverse waves, and all EM waves travel at the speed of light. So please remember those things. Right. Final question. Cool. Let's do this question. Um, because I have this question. Come your Omar doubles, right?
Okay.
Yeah. A doubles with slide. Don't put any sweet sauce. Otherwise, it's my ops. Yes, put sweet sauce in the doubles.
No.
Who here does put sweet sauce in the doubles? That's a real question. Who does do that?
Easy.
Yes, boy. Danielle, you just put sweet sauce in your doubles?
No, sir.
Nah, nah. I mad people thing, and let me not judge
Yeah.
anybody and their preferences. I personally hate ketchup. I hate ketchup, and people just call me a madman for that, but I hate ketchup. So I'm not going to say anything about you, Zachary. You do you on your sweet sauce,
The
right?
don't inspire though.
It is personally make me vomit, but like everybody different. Everybody is different, and that's fine. Yeah. So let's just do this question quickly. So Ambika, give it a read for me.
Humans can see electromagnetic radiation only between the wavelengths of about 4 by 10 to the power of -7 meters and 7 by 10 to the power of -7 meters. This is called the visible part of the spectrum. A rattlesnake can detect EM radiation of frequency 3.5 by 10 to the power of 14 Hz, and a honeybee can detect EM radiation of 1 by 10 to the power of 15 Hz. Calculate the wavelengths corresponding to each frequency.
Yeah, how much are you feeling cooked after reading that? How much are you feeling cooked? How much are you feeling cooked? If you're feeling cooked, Alma, be honest.
Me.
I like the honesty. I like the honesty. The honesty is what I'm going for. All right, so humans could see electromagnetic radiation. So first things first, this question dealing with electromagnetic radiation. If it's dealing with electromagnetic radiation, right? What is the speed of all EM waves? Let's get that out of the way. What is the speed or velocity of all EM waves? Do you guys remember? All EM waves travel at what speed? Because they will not tell you this in the exam. And if you don't know this, you can't do anything.
3 by 10 to the power of 8.
Yes. Ambika, you know that, right? All EM waves travel at the speed of light.
Yeah.
I can remember that, right? If it's electromagnetic radiation, just know speed of light. And the speed of light is 3 by 10 to the power 8 meters per second. Now we could proceed. So a rattlesnake could detect EM radiation with a frequency at this. So frequency here. So the frequency for this one is 3.5 by 10 to the power 14 hertz. Okay. And the honeybee could detect a radiation of 1 by 10 to the power 15 hertz. And what do they want us to calculate? Guys, what do they want us to calculate?
The wavelength.
Right. They want us to find wavelength. Guys, is there any formula that comes to mind here? You see in frequency. You see in wavelength. See in velocity. Is there any formula coming to mind?
V is equal to F lambda.
Perfect. V is equal to F lambda. Now, we want to find the wavelength. So if I want to make wavelength the subject of the formula, I would divide both sides by what?
Frequency.
Yep, I would divide both sides by frequency. Ambika, you seeing that?
Yes, sir.
Right, so lambda is equal to V over F. Do we know what the velocity of the EM waves are? Yeah or no? Guys, come on,
Would
yes.
it be the would it be the 3 by 10 to the power 8?
Yeah, that is what it would be. That is what it would be. Right? It would be 3 by 10 to the power 8. Right? Because it travel all EM waves travel at the speed of light. Cool. And so which one do I want to do first? Actually, let me just do the rattlesnake first. Rattlesnake. So for the rattlesnake, the wavelength is going to be the speed of the light. The speed of light, because all EM waves travel at the speed of light. So the velocity here is 3 by 10 to the power 8. And what is the frequency of EM radiation I can see? Come on, guys. What frequency of radiation could the rattlesnake see?
0.5 multiplied by 10 to the power 14.
And that is it, you know. You just have to plug it into the calculator and you get your answer one time. Danelle, you know what's plugged into the calculator?
No, sir. Because I don't have one of the Casios as yet.
You have a sharp?
No.
You have any calculator?
Uh, it's just one of the normal scientific calculators.
I can see it.
It's what is this? Oh, this is the Sharp Small Scientific Calculator.
The small one.
Yeah.
Oh, okay. Let's see if I could help you. Right. Okay. So this is what you're gonna do from right now. You're gonna open a bracket and you're gonna put 3 multiply by 10.
Multiply by 10.
You see in a button that says X shape, X like a little Y on top.
Uh, X, I'm seeing X with a square root of Y.
Hmm. Wait a second, I can look in for the calculator you have.
Right. So
Yeah, you're
is it
looking.
B?
Wait a I'm looking for the button. Oh yeah. Okay, you instead of seeing X, Y, you would see Y to the power X. You see now Y with a X. It should be right next to
Yes,
it
I
should
see
be
it.
right. So you are going to press that button and I believe a little thing like that should pop up. Is that popping up?
No,
What is popping up?
nothing. It just mark degree and the brackets on top.
Wait, so open bracket 3 multiplied by 10, and then you're gonna press the Y to the X button. Let me show you what I'm talking about. Mm, wait, so this is the Y to the X button I'm talking about.
Yeah.
Yeah, when you press that, you're supposed to see like a upward arrow pop up.
Nah, sir, I'm not getting it.
You can show me a picture where you're seeing, or like point your camera and show me.
Oh, okay.
But anybody get an answer?
So
And
what do you mean by video? You see my calculator?
yeah, let me just give me a second. Mm,
So it will be
right. So open bracket,
oh, open brackets
3
3
by
multiply by 10.
10.
Sorry. 3 multiply by 10. Uh-huh.
Right, then
I'm
press
pressing
that
here?
button. Yeah, press that.
No,
Put it.
nothing.
That's okay. Put it. Press it. Press it.
Oh,
Press. All right. Then press equal. Right. So it did work. It did work. Right. Then you're gonna press divide, and
mm-hmm.
now we're gonna put in the bottom part. So put 3.5. 3.5.
0.5.
Right. Multiplied. Press the multiply button.
Mm-hmm.
Right. Then you're gonna put 10. 10. Press 10. Then you're gonna press the Y to the X button, and you're gonna put 14. Press 14. Press equal. And that's weird.
Okay.
Oh, what did you guys get?
I'll practice this for the oh someday.
That calculator is weird. Very sus. Hmm. Yeah. You need a new calculator. That calculator is trouble because the calculator does share much on the screen, right? Let me plug it into my calculator there. So that'll be 3 by 10 to the power 8. Okay, you get answer.
Yeah, I did.
You should have gotten 8571. Oh, I can't know why you didn't get it, you know. I tell you 14 instead of 4. No, no, it's supposed to be 14. Yeah, my
No,
bad.
I put in 14.
Yeah, okay. When you put 14, oh, my God, the calculator can't go to that degree of that. It can't do all of that calculation. I know this said E. Yeah. So, then no, the calculator can't go up, can't do that calculation. That's why.
Oh, okay.
All right. Yeah. So, Mika, if you run out of the three decimal, I mean, three significant figures or two decimal places, what would you get?
8.571.
The two decimal places would be
Oh,
0.57. That would be by
yeah.
10 to the power minus 7. And where's the units?
It'll be in wavelength. So that would
Right.
be
Length.
so meters.
Right. Meters. Okay, now let's move on to the honeybee. Honeybee, right? And Danelle, I want you to help me with this. And you'll see how easy it is. Right, so Danelle, we want to find for wavelength. We already have the formula. So the formula for wavelength is V over F. So Danelle, all EM waves travel at the speed of light. So where's the velocity? Tell me Danelle.
What's the oh 3 by 10 to the power of 8.
Right, and all honeybees could detect EM radiation of what frequency?
1 by 10 to the power of 15.
So all you had to do now is just plug that into the calculator and you just would have secure yourself 5 marks. Easy, right? Plug that into the calculator, guys, and let me know again. To two decimal places, please. Did anybody get an answer? Quick, please. Right. One second.
I got 3 by 10 to -7.
Okay, I'll check that just now. Okay, you got 3 by 10 to the power 7, right? 3 by 10 to the power minus 7. And because I'm fast, you got that right?
Yeah.
Okay, great. That's your answers. Easy or hard? And because you think you can figure it out easily, no?
Yeah.
Yeah, it's just anytime you see EM radiation, just know the velocity is 3 by 10 to the power 8. They're not going to tell you. They expect you to know. Right? Look, they tell you. Damn. They tell you the speed of light was that. But you might know how to do that. Alright, thunder is heard 2.3 seconds after a flash of lightning is seen. If the lightning strike is 750 meters away, calculate the speed for this event. Right. So guys, if I want to figure out the speed, do you remember the formula for speed? Speed is equal to what? Does anybody remember the formula for speed? This is maths. Speed is equal to what over what? Think think simple maths. Nothing complicated.
Distance over time.
right? How far was the lightning strike?
$750,
Right? And what was the time taken for you to hear it?
2.3 seconds.
What is 750 over 2.3? Yeah. Yeah. Yeah, what is 750 over 2.3? Guys? Okay. Should get 326. Right, so that's the answer. So that's gonna be 326.09. 326.09. And speed is measured in what? What is speed in physics measured in? So it's distance. What do we measure distance in physics? Distance is measured in what?
Meters per second.
Right, distance is measured in meters and time is
I mean,
seconds.
what
So,
is it?
yeah. Right, basically the correct thing, right? So meters per second. Meters per second is your final thing. Great. And that's the answer. Oh, it's so easy just to get marks in physics. Like this is 5 marks and this is 4 marks. That's crazy. That's real crazy. Like in maths, you had to like kill yourself to get some marks. In C-Sec maths is like you had to kill yourself to get marks, but in physics is like easy marks. So yeah, because again, you owe my double to this question coming. I have a strong feeling this question will come.
What year was this?
I don't know what year it was, but I know it's gonna come. I can't. I don't know what year it was. I definitely a past paper question, but can't tell you the year. I'm not sure. Yeah, I'm not sure. In the Waves and Optics document I sent you, there's more past paper questions, so you could go and check that as well, right?
Okay.
And I have a 17-hour marathon document. I think I would have sent that to you guys. You'll have it. The 17-hour marathon document with everything in the syllabus. You'll have that.
Yeah.
Okay, for those of you guys that don't have it, I'll send it back. Great. So yeah, guys, that is it for today. Hope you have a blessed day. Enjoy your Saturday. And yeah, later, guys. Take care.